Let's look at an integral from probability theory that we can actually compute using the polar coordinate transformation. So we're going to start out with this integral. I is equal to the integral from negative infinity to infinity of e to the negative x squared over 5. Now when you study this with the normal distribution, this 5 will actually be replaced with a 2. But that's okay, the technique is still the same. This is just changing it up a little. Okay, so in order to use the polar coordinates, what we want to do is look at an additional copy. So we want to look at I squared. So we take our favorite variable other than x, which is y, and write the integral again. Now, in order to move this forward, we just push everything together. We write this as a double integral. And so using the laws of exponents, multiplying this term by this term will give us e to the negative x squared plus y squared over 5. So again, we have a very convenient integrand, and then of course the region of integration is the entire real plane. Now that's not very useful as it is, and it's certainly staying in Cartesian coordinates would not be anything that we could work with very well. So this is where we make the transition to the polar, because we can easily describe the real plane with polar coordinates. We can let theta run from 0 to 2 pi and then r from 0 to infinity. And that's a much more convenient description of the real plane. Now, in order to make the transition from Cartesian to polar, we use the change of variables. So our area element dx dy becomes r dr d theta, and our new limits of integration 0 to 2 pi and 0 to infinity. And then of course the x squared plus y squared is just r squared. So we have a very nice, neat integral in terms of polar coordinates now. Okay, now of course there's no theta dependence here, so we can just break this up into two pieces. The d theta integral will give us this, 0 to 2 pi d theta. That's a very simple integral. And now, of course, here this r is really going to keep us from going crazy. We need to use the chain rule. So when we look here, we don't have a negative 2/5 with the r dr. So we put that in, and then we pay for it here to make this integral table ready. So now this integral just becomes theta evaluated from 0 to 2 pi, which is just 2 pi. And now, of course, the integral of the e to the u du is just e to the u. We like that. We just get e to the negative r squared divided by 5 times the factor negative 5/2. And now, of course, this is an improper integral, but now that we've graduated, we can use a more convenient notation like they do in engineering and physics. So of course here, the 2's absorb and leave us a negative 5 pi. And now as we evaluate, basically we're letting r pass to infinity. So that's essentially e to the negative infinity. And then of course the lower limit, we have 0. So this is just minus e to the 0. Of course this converges to 0, and this is just 1 by definition. So we get negative 5 pi times 0 minus 1, which gives us the positive 5 pi. And now, of course, this integrand is non-negative, so we extract the positive square root. So our original integral, is just the square root of 5 pi. That's an amazing calculation that we can do with polar coordinates. And we are done.